All right, open up your book to section 1-4. Section 1-4 starts on page 23 in your book. And the title of this section is Composition of Functions. The objective here is given two functions. We want to be able to graph and evaluate the composition of one function with another. Graph and evaluate the composition of one function with another. All right, so let's start out with a definition here, just so that we know what a composition is. When we talk about a composite function or a composition of functions, here's what we're describing here. We've got a function that's in the form of f of g of x. F of g of x. X is your input there. You'll plug that into function g, and then that result becomes the input now for function f. And you plug that into function f and get another output. All right, so it requires you to plug in a value a couple of times into perhaps different functions in order to get your result. So it's a function in the form f of g of x, where function g is called the inside function. I think that's obvious because it's inside the parentheses there. And function f is called the outside function, and that's because it's outside of all those parentheses. Those are the names we give those two functions there, the inside function and the outside function. A couple things on notation here. First of all, when you see this, we read it as f of g of x is the way that that's read off. F of g of x. And again, the notation there is f followed by a set of parentheses, and inside that you write g of x. And again, the way that you evaluate that is you start out by plugging in a value for x into function g. The result you get for that becomes the new input that we're going to plug into function f in order to get the final output that we want. There is actually a symbol or an operator that we use to represent a composition in mathematics, and this is it. It's that open circle that you see there, that little open circle. F composed with g of x is what we see there in that third bullet. Or you can actually put the composition in parentheses first and say it's f composed with g of x is the same thing. I like writing it in that first form that you see there. I'd probably get used to writing it as f of g of x using just the parentheses. So if you see it in one of the other two forms, just rewrite it that way. But again, just so you recognize the symbols that we'll use for composition, there you go. It's that little open circle. All right, let's take a look at the first example here. There's actually several examples that we need to go through. On page 25, it says you've got functions f and g. They're in this graph here. I've got them both sketched up here for us. And they want us to find the composition f of g of 30, showing on copies of the graphs how you found this value. Okay, so f of g of 30. F of g of 30. All right, so you have to start on the inside. You work on from the inside out is how we've got to evaluate this. So this is saying take 30 and plug that into function g. That's what it's saying to do there first, that part right there. So g of 30 is what we've got to think about evaluating first. Ignore the function f out front, in other words, to begin with. So the question is, what do we end up with g of 30? Well, start with this graph that we have on the left. They've already marked this value of 30 for us. That's our starting point. Okay, and the question is, if we go up to the graph, the question is, where exactly do we end up with, if we go horizontal? That wasn't quite horizontal, that's close though. If you go over to the y-axis, where exactly are you at? Now, if you need to look in the book to get a good approximation for that, rather than my sketch here in this video, then do so. But it looks like that's probably about, it's more than halfway between 2 and 3. I'd probably say it's probably 3/4 of the way between 2 and 3. So I'm going to say that this is equal to 2.75. We're just approximating it. So it's okay if you thought that was 2.7 or 2.8. Even if you probably said it was 3, that's probably fine as well. Okay, just try to get roughly a good approximation there for us. So now what I can do is I can take that value of 2.7 and I can replace that in function in this composition. So this is equal to f of, and I can replace g of 30 here with this 2.75 now. That's what goes in there. So I've taken g of 30 and replaced it with what it's equal to. Start at the inside and work your way out. Now I've set up another problem for me to solve. Now I have to look at my graph and I have to find out what's happening on function f at x equals 2.75. So I got to find 2.75. That's going to be about right here, we'll say. This is 2.75. And the question is, what is our function doing at 2.75? And it comes over about right there. Again, try to be as close as you can there, but it definitely looks like I'm somewhere between 100 and 200. Looks like I'm more than halfway there. Maybe I'd even say I'm 3/4 again. So I'd probably say that this looks like this is about, what, 3/4 would be what, 175? That's what I would approximate that to be. So I would say that this looks like this is equal to 175. Actually, I'll do that in red as well, since that's what I have up above. So that would be my approximation there for f of g of 30. All right, plug in a value into function g first, and then take that result, plug that into function f. That gives me my final result, the composition of those two functions. All right, let's take a look at another example here. Example number 2 on page 26 in your book. This time, instead of giving us a graphical representation of a function, they're going to give us a numerical representation of a function, a table of data. So they've got a function f and g there identified for these integer values in the table. So for part A, it says find f of g of x for the 6 values of x in the table. I don't know if we're going to go through all 6 of these, but we can at least go through some of these. Let me add another column to this. We'll call this, which way do they want us to do the composition? F of g of x. Make sure you do the composition in the right order, because order does matter here. F of g of x. All right, so f of g of x. So if I plug in x equals 1, that would be f of g of 1 is what I'm looking for. And so f of g of 1, again, the place to start here is you got to start out at x equals 1, and the question is, what value is function g at x equals 1? So that's looking over here at this value of 5. So g of 1 is equal to 5. So I can write this as f of 5. I guess I'll put that in red there just so you can see how that fits in there. So that's f of 5. And now what I got to do is I then got to find out, okay, what's happening at x equals 5 on function f. So I go down my table, here's x equals 5, and I'm wondering what's happening on function f. That's the second column there, so that looks like that's a 0. So this looks like this is equal to 0. So f of g of 1 is equal to 0. That's what I end up with. All right, so that's what we're trying to do here in this example. Let's do the second one here. So if I want to do f of g of 2, I won't worry about going through the colors here, but if it helps you to draw this out, then do so. G of 2, so plug in, go down to the second row in your table and all the way over to the third column. G of 2 is equal to 3, so this is f of 3. And now plug in x equals 3, go down to the third row into function f, the second column, that's 6. There we go, f of g of 2 is 6. Let's do the next one as well. So f of g of 3. So g of 3, so in the third row, g of 3 in the third column there is 2. So this is f of 2. And now take and plug 2 into function f. So go to the second row in your table, over to the second column, that's a value of 4. You see how we can use our table there to come up with these values. All right, let's skip a couple. Let's jump down to f of g of 5. F of g of 5, so again, starting in row 5 here then, plug in 5 into function g, that's the third column of our table, that's 7. So this is equal to f of 7. And then when I go to plug in 7, oh, there we run into a problem, don't we? This all works great as long as these numbers all show up in my table, but I just ran into a problem that there is no row 7, so I can't find out what f of 7 is equal to. So this does not exist, or it's undefined. Okay, based on the data they gave us, I can't tell you what that value is equal to, so it's undefined. All right, that was the first part of this one. They said to do all 6. I've done most of those. You can fill in the rest. Part B says find g of f of 2 and show that it does not equal f of g of 2. Well, we already found f of g of 2 up above. I guess I'm going to do this down below here now. Let's do the composition the other way around. I mentioned that earlier when I was writing this down. It's important you do the composition the right way because order does matter here. So what happens if I do the composition this way? F of 2. What's f of 2 equal to? F of 2 is equal to 4. That's the second row and second column. So this would be the same as g of 4 that we're trying to calculate. And g of 4, if I plug in 4 into function g, I get a value of 1. Okay, so when I compare those two, I can definitely see that I'm not getting the same result here. Here I get a value of 1, but up here I'm getting a value of 6. Definitely not the same thing. All right, some functions we will find that that is the case, that they are the same, but most functions, if you do the composition the other way around, you get a different result. So order matters there with those compositions. All right, let's take a look at the next example. Example 3. This time they're going to give us a algebraic representation for a function. So we've seen a graphical, we've seen numerical, now an algebraic representation. That is, they're going to give us an equation here. They give us a linear function for function f. F of x is equal to 3x plus 5. And g of x is an exponential function. G of x is equal to 2 to the x power. All right, so we got ourselves an exponential function for g and a linear function for function f. All right, and they're going to ask us to do some compositions here with these two functions. So take a look at part A. Part A says to do, well, they're going to ask us to do 3 here. I'm going to just, again, I'm going to pick and choose, I guess, the ones I'm going to do. But let's do the first and the last composition they asked. You can do the other one if you want a little more practice there. You've got f of g of 4 is what they're asking you to do. And unlike the table of data where we were limited on what we could actually, what values we could plug in because I was only looking at a small table of data, here I can pretty much plug in any number that's in my domain. As long as it's in the domain, I'll get a result here. So what do we end up with? If I plug in 4 into function g, that's that exponential function. So I'll end up with 2 raised to the 4th power. 2 to the 4th is 16. So this is the same as f of 16. And if I plug in 16 into my linear function, what, 3 times 16 is what, 30 and 18? That's 48 plus 5. Sounds like 53 is the value we should end up with. Okay. Let's also do f of g of negative 1. So what do we get when we plug in negative 1 into function g? We end up with 2 to the negative 1. 2 to the negative 1 is the same as 1/2. So this is going to be f of 1/2. I'll write it that way. And then when we plug in 1/2 into function f, 1/2 of 3 is 3/2, or 1.5 if you want to look at it that way. Plus 5 would give us 6.5, right? I'll write it as 6.5. Should be the value we end up with if we plug in negative 1 into f of g. All right, look at part B on this one. This one says find g of f of negative 1 and show it's not the same as the same value we just came up with. All right. Well, we've already done this on one problem, so it shouldn't be a surprise here on this one, but let's just compare in this case what we get. So if I do the composition the opposite of what I just did, if I plug in negative 1 into function f first, I get a negative 1 times 3 is a negative 3 plus 5 is 2. So that's g of 2. And g of 2, when I plug in 2 into function g, 2 to the 2nd power, that's better known as 4. And so, yeah, I can definitely tell that those two values are not the same. Here I got 6.5. Here I got a value of 4. We're getting different results based on the way you do the composition. All right, and then for part C, it says find an equation for h of x that they're calling the composition of f of g of x, which they wanted explicitly in terms of x. So that means we got to do a little bit of more algebra on this to get this result. So they said h of x is equal to f of g of x. Again, make sure you got that composition the way they ask you to do it in the problem. And they want us to find what this is equal to. So let's do a little bit of substitution, similar to what we just did up above, but instead of plugging in numbers, I'm going to be replacing these with the function. So g of x, there's nothing I can do to simplify that. Just simply replace g of x with what it's equal to. G of x, the inside function, is 2 to the x power. So I write that as f of 2 to the x. And now I take that and I plug that into function f. And again, function f is that linear function. That was what, 3x plus 5. So I'm going to replace the x that I see in there with 2 to the x. So it's going to be 3 times 2 to the x plus 5. And remember your order of operations here. Don't be multiplying that 3 times the 2, because the order of operations tells me the exponent gets taken care of first. So this is not the same as 6 raised to the x power plus 5. All right, that's completely different. 3 times 2 to the x plus 5, I can't simplify that at all. That's the way I'll have to leave it. And they also said then once you do that, show that h of 4 agrees with what you found for f of g of 4. Well, I guess we did that in part A, so let's verify that h of 4 again would be the same as f of g of 4. But if I take this function that I've got here and write and calculate that out, I'd have 3 times 2 to the 4th plus 5. Let's see what we end up with here. So 2 to the 4th is 16 times 3 is 48 plus 5 would give us 53. And so what happens when we compare those two values? Here I got 53. Compare that with f of g of 4 up here. I got 53. Yeah, those check out. Those are the same result. If you turn to example 4, they give you the same problem here. They ask us to do a couple more compositions, and I'm going to do just one more here, I guess. It's that first one they ask you to do for that example. It's the composition of function f with itself, just because that's a little bit different. I'll call this d, even though there's not a part d for this, but f of 2 is what they ask you to find there. f of 2, just so we can see how we deal with this. If it's not two different functions, how does that change things? It doesn't. You still do this the same way. It's just what function you're plugging these values into. So this says first start out by plugging 2 into function f. Okay, well function f again is this function 3x plus 5. If I plug 2 in there, I get 3 times 2 is 6 plus 5 sounds like 11. So this would be the same as f of 11. Again, I'm replacing the f of 2, the inside part there, with 11. And now I do the same thing. Now plug 11, though, into the same function. So again, function f is 3x plus 5. So 3 times 11 is 33 plus 5 sounds like that's going to be 38 is our result. All right, just realize that it doesn't have to be two different functions that we're working with when we talk about this composition. And if you want to do the second part of that example, they're just showing you that you can keep going with these compositions. F of g of f of negative 3. All right, there's no limit on how many times you can do a composition there. All right, let's take a look at one last example here. This one they gave you 2 graphs, but then well, they actually ask you to redo some stuff that you've already done. In part A, it says show on copies of the graph what happens if you calculate these 3 things. Well, we already did that in the first example. We were given a graph and then said find these compositions. So we've done that before. I'm not going to redo that. Part B says to make a table of values, so they're looking at it from a numerical approach. Well, we just did that in example 2. So I'm going to skip over parts A and B, but certainly if you want to try those, you could certainly go back and try those out. Let's take a look at parts C and D. This gets a little more interesting, that they actually give you these 2 functions. They tell you what g of x is and what f of x is. So I'm going to write those down. For part C, they said that g of x, that's the graph over here on the left, is equal to x minus 3, and it's on a restricted domain. It's from 2 to 7. And f of x is another linear function. That's a negative 2x plus 8. And again, it's on a restricted domain from 1 to 5. And this one here says plot the graphs of f, g, and f of g of x, that composition on your grapher, with the grapher's grid showing. Does the function f composed with g confirm what you found numerically in part B? Well, we're going to do that in a second. And what is the range of f of g of x? All right, so let's graph these. So grab your calculator. All right, so on our calculator, in Y1, let's go ahead and put this, I guess I'm going to do it in the same order that they've got them, but I got to be careful here as I do this because they gave us g of x first, so just keep in mind that when we go to do this composition here. Oops, I'm going to put this in parentheses. The parentheses are optional technically, but I like adding them in there. So we've got x minus 3, and again, we're going to divide that by our domain, which is from 2 to 7. And that's under your test menu. Again, I'm going to grab the conditions because I like that feature there. It automatically has all the extra stuff I need there. So I can just put in my 2 and 7 in there. And then negative 2x plus 8. And we got to divide that by its domain, which is from 1 to 5. All right, so make sure you get those put in there correctly there. And I'm just going to sketch these to start off with. I guess for the window here, I'm going to kind of steal the graphs that they gave us there to start off with. Let's go from negative 1 to, I think they went out to about 9 there in their sketches that they gave us. And for our y values, probably if we go from like negative 3, I'd go a little bit further down than what they gave us. And I think if we go up to like 7, that should give us a decent window to see this in. Okay, so there's the two graphs that they gave us there. And then they asked us to find f of g of x. Okay, so I'm going to also sketch that along with it. And we can do a composition, just like we were using with dilations and translations in our transformations section earlier. We can do a similar thing here using function notation. So f of g of x, but again, the key is you got to remember which one's which. F was function y2 for me, so it's going to be y2, and then in parentheses, y1, and in parentheses we'll put the x. Technically, you don't have to use the parentheses x, but I like putting it in there so it looks just like function notation there. And let's graph that. And what's interesting here, you end up with a linear function. That might not be a surprise for us, although that doesn't happen every time. That just because you start with certain types of functions doesn't mean that's the type of function we're going to end up with there. But notice the domain has changed. The domain's quite different from the other two functions we started with. All right, so we've graphed these. That's the first part of this. And then does the domain confirm what you found numerically? Well, we're going to find what the actual domain is here. I can tell already it looks different. What's the range of this function? Well, it looks like once we find the domain, that would help us with the range here, but we'll use our calculator to help us out a little bit here. If we go to trace, and I will go to y3, it looks like it starts out with an x value of 4 and a y value of 6, and then it goes to what? Looks like it ends there at 3, or not at 3, it looks like it ends there at the x-axis. What value is that? It looks like that's at 7 probably. So it looks like it goes from 4 to 7 in terms of the domain, and it looks like the range is from 0 to 6. Let's write those down. I'm going to grab a picture of this while I'm at it. All right, so our domain we said we're going to verify this in a second, but it looks like our domain is from, what do we say, 1, 2, 3, 4 to 7. And it looks like our range was from 0 to 1, 2, 3, 4, 5, 6, right? 0 to 6. And that's our y values. That looks like what we end up with, okay? So let's see if we can verify with this, which is what Part D asks us to do. Part D says find the domain of this composition algebraically and show the degrees with Part C. So that's what we're going to try to do here, see if we can actually find this actual domain algebraically. We did it graphically using our calculator to help us out here. Let's see if we can do it algebraically. So to do it algebraically, again, you're looking at the composition f of g of x is the composition we're looking at it. They use the composition character there, or the symbol, and you can leave it that way if you like, but you might want to switch that over to this notation here. All right, so there's two things to deal with here in order to find this domain. The first thing that we've got to do is we've got to start with the inside function. That inside function is function g, and you're plugging x into function g. So I'm taking x and I'm plugging that into this function right here. So I have to consider what's the domain for that function for the values I'm plugging in there. I'm plugging x in there. So the domain of g, we'll call this. Domain of g. We're plugging x in there. So that says that I have to plug in values of x that are between what? What was the domain of that function? For function g up here, they told us that the domain was from 2 to 7. Whatever you plug into function g, whatever I plug in there, has to meet this criteria. Has to be between 2 and 7. All right, so from that, I can state that I know that x has to be between 2 and 7. If you want to plug in a value outside of that, it's not going to work. Can't plug in anything outside of the range from, or the domain from 2 to 7. Now, the next thing you're going to do is you're going to take that result. I'm going to take this whole result and I'm going to plug that into function f. But notice I'm not plugging x into function f. I'm plugging g of x into function f. So now let's consider what the domain of f is based on what we're plugging into it. So for the domain of function f, let's go back up here and refresh our memory what we said about function f. Function f, this says that if you're going to plug x into function f, then it has to meet this criteria. X has to be between 1 and 5. But again, we're not plugging x into function f down below. We're plugging g of x. So g of x is what's going to have to be on that interval from 1 to 5. So let's write that down. G of x is going to have to be between 1 and 5. That's a big difference there between these two lines here, right? First one was x was between 2 and 7. There's nothing else to figure out there. We already know what the domain is. Here it's g of x that has to be between 1 and 5. I still don't know what that means about x, so let's go and replace function g of x in this double inequality with what it's equal to. G of x again is the function x minus 3. So I'm going to say that that means that x minus 3 is what has to be between 1 and 5. And now simplify this. I basically want to get x by itself in the middle here, so I'm going to have to add 3 to everything. So adding 3 to 1 gives me 4. Adding 3 to x minus 3 gives me x in the middle, which is what I wanted. And adding 3 to 5 will give me a value of 8. So that means that x has to be between 4 and 8. And so now with these two domains that I've come up with, this guy right here and this guy right here, I have to figure out what do they have in common. Whatever they have in common is my result here that I'm looking for. So there's a couple ways you can think about this. You could actually graph these on a number line and just find out where they overlap from 2 to 7 versus 4 to 8. What's the overlap? Or the other way that you can do this is if you look at the lower bounds, these two values here, you have to pick the bigger of those two numbers. So that would be 4. And then do the same on the upper bound, but for the upper bound, look at your two values, the 7 and the 8, and you have to pick the smaller of those two. So that's the 7. So the resulting domain here, if I fill in the rest of my interval here, do that in black, 4 has to be less than or equal to x, which has to be less than or equal to the 7. And if we compare with what we just saw there on the graph, that's what we set up above there. When we looked at the graph looks like it has a domain from 4 to 7. When we actually work it out algebraically, it does have to be from 4 to 7. That's how we actually find these algebraically, is considering these two separate domains and then looking what they have in common. That tells us the actual domain we're working with. All right, a couple last things here. On the last page of this section here, they give you a little box that has some properties and so forth, and we should discuss those here. So for the domain of compositions, the domain of f of g of x is the set of the following values. It's a set of all values of x that are in the domain of function g for which g of x is in the domain of function f. Again, there's kind of a two-step process there you've got to consider when you set this up. The domain of f of g of x is a set of all values of x that are in the domain of the inside function, g, for which g of x is in the domain of that outside function, function f. That's what we just went through on that last example. We had to consider both parts there and find all values that those two had in common. Visually, we can kind of represent it this way. Let's suppose that these circles or ovals, I guess I've got here, represent the domains and ranges of my two functions. So I've got the domain of function g on the left, and then the range of function g in the middle there. And then I've got the domain of function f there in the middle as well, and the range of function f over there on the right. And in the middle there, there's some points that these two share. These ovals are going to represent all of the numbers, all the values that correspond to the corresponding domains or ranges of those particular functions. And it turns out, when I look at the range of function g and the domain of function f in the middle, there's some places that they'll have in common, some points they'll have in common, and other points that they won't have in common. And so let's consider what happens here with a composition. Let's just illustrate a couple of examples here. Let's suppose that I take some point right here, we'll call him x1, and I plug him into function g. And let's suppose that when I do that composition, that point lands right here. This right here is g of x sub 1. When I plug this into function g, I end up there. Now, because I landed, obviously, in the range of function g, but I also landed in the domain of function f. That's the overlap between those two ovals. That means since it's in the domain of f, I can take that value and I can plug it into function f, and I can end up with some point over here that will be f of g of x sub 1. Right? Well, every time we did a composition and we were able to plug in a value into g and then plug that result back into function f and get an answer, this is what was happening. Sometimes, though, you run into problems, and we saw this in a couple of our examples here, so let's illustrate what could happen here. Sometimes, let's pick a point right here, x2. Sometimes I take this point x2, and of course, if I plug it into function g, I have to land somewhere in its range. Let's suppose that I land right here. So when I plug this in here, I end up with, when I plug this into function g, I end up with this point right here, which is g of x sub 1. Well, that's great, but notice that that's not in the oval representing the domain of function f. That's slightly over to the right further. So in other words, I can't take that value and plug it into function f and get a result. Sometimes that happens. Or perhaps you even end up with this problem. Maybe we pick a point, let's say x3 is down here. x3 is not even in the domain of function g. So I can't even plug it into function g to get a value out of that function. That's a problem as well. Visually, this is what happens when we're doing a composition. Sometimes, like you see in red there, we get values that we can dump into each function and get a result at the end. Sometimes, like you see in blue here, I only get a value from the first function, the inside function, but I can't plug that result into the outside function. Or maybe, like we see in green here, I can't even plug that into my my inside function, g of x. So just one last note. What you should notice here from this little example. F of g of x sub 2 is undefined since g of x sub 2 was not in the domain of f. All right, oops, I mislabeled that. Sorry, let me change that. I called him x sub 1 there. He's actually x sub 2 at this point. G of x sub 2. Okay, that's the point we're talking about, that he does not lie in the domain there of function f, your outside function, so I can't get a result. And on the other hand, f of g of x sub 3 is undefined because x sub 3 was not even in the domain of function g, so I couldn't even evaluate that in function g. So I definitely couldn't plug anything into function f then either. All right, that right there is section 1-4.